Well, welcome. This is Mike Dohm. I'm a biology professor at Chaminade University, and I thought we would go ahead and talk a little bit about statistics, and more specifically, statistical thinking and how it relates to forensic science. So, this is the first part of four total videos that I've produced for you. So, let's get started. All right. As I mentioned, four videos so far. I teach a biostatistics class at Chaminade, have for a number of years. And so I could cover a whole bunch of stuff. This is, one of my specialties. This is one of my passions. And I believe very strongly that a good foundation in statistics helps you in whatever field you do. But in particular, statistics and statistical thinking is important in the law. And as someone working in forensics and in particular working with DNA, being able to understand the probability calculations that you do, statistical thinking is an essential part of, I think, what you contribute. So how we're going to proceed through this is I'm going to go ahead and assume that you have very little statistical background. I am going to sort of mirror some of the things that I do in my biostats class, including making some suggestions about loading some software onto your computer so that you can start doing statistics on your own. All right, so the four videos are more or less lined up with setting up your resources that'll help you with learning statistics, and then we'll spend a little bit of time talking about statistics itself, and we'll break it down into a couple of areas. The first part will be what we'll call data exploration, and that's the basics of describing your data and how to report your data. An example of how to report, of course, is the concept of data visualizations, better known as making graphs, right? We'll spend some time talking about probability, and we'll introduce you to the various hypotheses that stats people talk about and how to interpret the results of tests, of assays. For example, how to interpret the results coming out of a DNA profile. We'll also have to talk specifically about populations and in population genetics, and in other areas we like to talk about subpopulations. And you should appreciate that this is a much more nuanced subject than we commonly think. For example, what do you refer to as a subpopulation? In the United States, we might be thinking about ethnic groups and whatnot, and so you should appreciate that these are not well-defined discrete units, and often the data that you're working with are based on self-reported, right? And so if you're to understand the DNA SDR profiles that go into this, there's some fuzziness between populations. And so what we would like to know is given these population genetic variables, how does this approach, how does this impact, how does this set limits on how we can report about match probabilities? After all, that's kind of the whole point about doing DNA typing, right, is to be able to exclude or include a sample from a suspect's profile, right? And so the last part we'll talk about match statistics and then introduce you to the idea of likelihoods. Okay, so you're working with, one of the big names in the business, all right? John Butler has been instrumental in doing some enormously important work about DNA typing, right? And so your book has a good discussion of statistics, but he's got a very strong opinion, and so there's some things that show up in Chapter 11, and then moreover in Appendix 3 that are kind of interesting from my point of view, where it's like, I hadn't really, that's not the way I would think about it. I'm not a criminal lawyer, and I'm certainly not a forensics expert and such, but as a epidemiologist and a statistician by training, took a lot of population genetics, and so some of these things, as they show up in your chapters, are interesting. We'll put it that way. So we'll touch on some of those ideas. I don't necessarily say that I've got this definitive viewpoint here that's just going to blow your mind, but it's some things to think about, right? So certainly Chapter 11, Appendix 3, we're going to be, you're going to hear, you're going to see, things will pop up in these videos that show up in those pages, all right? I'll go ahead and toot my own horn. I have, there's lots of statistics resources out there, ranging from, you can take, online courses. I have a couple of what I call, they're open source books, basically, where I've published my lecture notes in more or less a book form. And the main one is this, what I'm calling, really imaginatively, Mike's Biostatistics book. Okay, and it's hundreds and hundreds of pages of lecture notes, ranging from, I think, some interesting stuff to some very, very straightforward how to do statistics and particular statistical tests. Also, what you might be interested in is the workbook that I have there, in which I have hundreds of problems, some good, some in progress, okay, that I use to support my biostatistics class. And so both of these are the websites, both of them completely free. There's nothing you need to do. Just go ahead and click on them and start exploring it. Some of the slides that I'm going to present are straight out of my biostatistics book, right? I also So thinking about what you need for doing statistics, well, clearly, if you go work with the FBI, or you go work for a police department, or any of the institutions that work with DNA profiling work, they're going to have in-house software that's been validated and purchased, et cetera, et cetera. But you should appreciate that a lot of the research that went in to support that software is now absolutely done with the free software packages out there called R. Now, in our class, we also use a graphical user interface that works with R called R Commander. And so that allows you to have a drop-down menu to work with the statistics. And so after a little bit of a learning curve, it's a pretty seamless package to do statistics, ranging from very simple things to the most sophisticated things that you're ever going to see. So my recommendation is I want you to, think about, you go ahead and install R and R Commander or R Studio to your own computer so that you have it available. But you can also, and this is particularly in the data science fields, people like to run things in the cloud, and so you can run R as a Jupyter notebook, for example, or you can run it at Google has Jupyter notebooks, and other groups have one. So one of the ones I use is called CoCalc. So that is, you just set up your account and you can then interact with R via your own scripts and whatnot, and so you don't have to have it installed on your computer. That's fantastic, and in particular when you're working as part of a team, it might even be essential, right? But if you're going by yourself, I don't think that there's anything wrong with thinking about, well, what if I don't have internet access, right? So install software on your own computer. All right. So I have notes in my biostatistics book about how to install these things if you're interested in do so, right? Sort of also kind of justifying spending some time thinking about this. There's again an increasing use of R in forensic science, and so this is an example of hundreds and hundreds of pages of work talking about forensic science statistics and using R as the platform. So the title is Open Forensic Science in R. And if you can read that, that's the URL up there in the upper left part. Okay, so basically you're going to get your computer ready. You would go to, say, Project R, rproject.org to download. If you're on a Mac, most of you now are probably using the later Macs, not the old Intel base, but the little bit of twitchiness to that. You have to pay attention. There's good instructions, but you have to read the instructions. Always a good idea. Okay, and then most people use R in a platform called R Studio, which is now actually just in the process of changing their name, so we'll see what happens. Okay. Also, really recommend that you utilize your spreadsheet software. So many of you, when you purchase your computer, you got a license to use Microsoft Excel. Fantastic, all right? Some of you, through your high school experiences and whatnot, have been introduced to Google's free Office suite of software, including Sheets, which is their version of a spreadsheet. And Google Sheets is pretty good. The only thing about it, it is free, and it's very much like Microsoft Excel. It uses most of the same sort of commands and functions that you would find in Microsoft Excel. And the only thing about it, of course, is that it's online. So there's that. So I actually use LibreOffice, which is an open source group, produces a word processor that's Microsoft Word compatible, but I really like their spreadsheet called Calc. All right, so the advantage of this is LibreOffice is free. Microsoft Excel, to get the full package, it costs you a license agreement, and the license agreement, it can run as much as $100 a year, right? So while Google Sheets is free, it's got some limitations to it, and so there are other options besides Microsoft Excel and LibreOffice. That's the one I'm pushing, right? Okay. Some of you with Macs, maybe you use Numbers. Numbers is fine, and if you know anything about the history of personal computers, you'll of course recognize that Apple was the first to provide a spreadsheet. So yeah, my problem with Numbers is that it does things completely different from everybody else. And so you learn how to use Numbers. It doesn't translate to using Excel or Sheets. The functions are often buried and different. How you run it's a little different. Even though I use Macs all the time, I've never kind of adapted to Numbers. So if you use it, that's great, but there's a lot less help out there compared to using Excel, for example, or Google Sheets, right? Okay, so you need a spreadsheet app to handle your data, basically. If you're dealing with tens of thousands of data points, then more than likely you're going to be using a database, and more than likely that database is not on your computer, right? But spreadsheets are fantastic for working with data samples that are in the hundreds to a few thousand, and they're fantastic for manipulating the rows and columns. All right, and you can do all those things in R using commands and whatnot, but that's what spreadsheets are for, so they're actually much easier to use. All right, so install R. I recommend R Commander to help you kind of learn how to do statistics. It has a nice drop-down menu. I have about 10 mini tutorials that you step through to learn how to use R, and that's part of my workbook. Okay, and this is from my class. I have the first sort of homework problems that have to do with recognizing assumptions, so you might want to try that out. All right, so we're at the 16-minute mark, so I want to continue a little bit. We'll see if we'll speed this up. Let's go ahead and justify. Why R? Free. Open source. Open source means thousands and thousands of people are looking at the code, and so if there are problems with the code, people will recognize it. Things that are in part of commercial packages, bug reporting is a very standardized feature of that software and whatnot, but it's a much more a longer process of fixing things, and of course they're closed. You don't necessarily get to look at the code itself. So being good scientists, you should always have an appreciation for what your code's doing, and so you should be able to check it. All right, widely accessible, well respected, very, very good at making graphics, and can handle all kinds of different situations. And as well, you can create graphics that have never been developed before, depending on your needs. People have said to me, hey, it's really tough learning all this. I would just simply submit, learning any statistical software has a learning curve. So for example, you can do some statistics in Excel. The number of steps that you take to do simple statistics far exceed the steps that you do in R. Just saying, it's easier in R often, and both of them involve learning curves. The other advantage of learning R is that it's a recognized coding platform, and so if you're interested in freelancing, even after a semester or two working with R, you're qualified to do data entry level work in the gig economy. So this is the 5RR website, and so you can put up a shingle and say, hey, I'm ready to do some work. Right? Okay. Let's justify statistics in general, right? So why biostatistics? So from a perspective of doing DNA work, DNA profiles, more particularly if you're going to try to say the subject's profile matches the samples that we found at the crime scene, there's no way you can do this without statistics. Very convincing graphic I've got here, right? Okay, so what do you mean no? Well, okay, the match probability is a statistic. It's something that you estimate. All estimates are uncertain. We can quantify the amount of uncertainty. It's a probability. Okay, it ranges from 0 to 1. But we can never eliminate that uncertainty. All right? So the best we can say at the end is something along the lines of we're 99% confident in our estimates. So this is a comic from the XKCD guy, and yeah, all right. Uncertainty, let's talk a little bit more about this. You mean error, like mistakes, and it's like, no, it's not an instrument error. By the time a statistician gets the data, those errors have been dealt with. So as your book says, and certainly since it's been published in 2009, there's been an enormous amount of research about how to get genotypes out of sequence information, right? So when your book was written back in 2009, you're still basically using capillary electrophoresis. Now you do sequencing. And so looking at profiles and assigning bases to specific positions and whatnot, that's a technical problem. Statistics is used to sort of quantify how good, how accurate a base call is, but that's not the kind of errors that I'm talking about. It's not typos in the data. It's none of those kinds of errors, right? So uncertainty comes from the fact that you are sampling. You're sampling from populations, all right? So in a later video, we're going to spend some time talking about sampling. But for right now, I want to take you back a little bit in history, just very briefly. Statistics has a long history, but asking questions about data is a very recent stop in our travels through science. All right. I don't know if you recognize this. This is cave art from about 10 to 12,000 years ago in Argentina. All right. So, read some books, right? Really good history of statistics. It's by David Salzberg. The Lady Tasting Tea. So some highlights of this. Mathematics certainly goes back well before 2000 BC, but probability, which is the foundation for what we call statistics and statistical thinking, comes much, much later. It really only was fully developed in the very late 19th century. So it's a very recent thing, all right? In antiquity, what we meant by statistics is governments started taking counts of everything. So ranges from, crop yields, particularly the census, of course, how many people are living under my domain, how much money am I bringing in? Okay, those all resulted in numbers, and so ultimately the word statistics refers to that, state numbers, right? The first life table, which is a really important piece of work, dates back just prior to the 1700s, Edmund Halley, okay? And looking back, we can find a little bit of work on probability as far back as 1550. And kind of the point I like to make about it was the motivation for probability was gambling, to make money, to understand how to beat the house, or if you were the house, how to assign odds, how to make money off of gamblers, right? And so it has kind of an unsavory history to it, which makes it kind of an interesting read. So the word statistics, it has two meanings. Classified facts representing conditions of a people in a state. That's one sense of the word statistics. The modern definition, though, statistics, any number that you estimate about a population or a sample. It's a description. It's an entity into itself. It's a statistic, usually singular, right? Statistics often, though, means, in the plural, it means that you're asking questions about data, okay? And statistical inference only really goes back to the first parts of the 20th century. Okay, so let's get you going on statistical thinking, and central to statistical thinking is the idea of probability. All right, so we have to define some terms, and what we really want to know is how likely is an event to occur. So a probability refers to basically what's the chance that something specific, an event, is going to occur. So an example would be suspect samples matches a crime scene sample. And of course our options are exclusion, inclusion, or inconclusive, right? More generally, you'll see in experimental work with humans on given two different drugs, which drug is more effective on lowering A1C levels. If you're alive today, how likely will you live until tomorrow? Those are statistical questions. A probability can be assigned. Risk of injury or death, passenger on an airplane versus car travel. Cities which differ for air pollution. What happens to mortality rate? Model the infection trends given virus reproduction number, vaccination and immunity status. So I just give some examples. The reproduction number of the original SARS-CoV-2 variant is about 2, so that means for every person infected, 2 people will be infected. The Delta variant, the number went up to 5, and the Omicron variant is one of the Omicron variants anyway. The reproductive number is as much as 7, so much, much more infective. Okay. How do you use probability to solve questions like this? Well, a person that you should be aware of in this is R.A. Fisher. And so his view about these kinds of questions is basically you have to be able to count all possible outcomes. And then you run your tests, your experiment, and you observe a result. And then you can say, how likely is my result in the context of all possible results, right? And I count how likely is my result to come. And if it's my outcome is rare, then I have some evidence that something is happening, not simply due to chance. Okay, so this is where the lady tasting tea comes from. This is, something that Fisher wrote about in his book, and whether it actually happened or not, it's really hard to say. And there's also going to be thinking about the British in the 1920s. This is going to be a funny sounding story, right? So a bunch of guys are in talking about science and whatnot, and one of them says, well, my wife says, and of course in the room there's no women, right? But at any rate, my wife says that she can tell the difference between tea where the milk has been added before the tea, or tea in which the milk is added later. And of course, being men, right, they're all going, oh, no, you can't tell the difference, yada, yada, yada. And so Fisher popped up and said, well, we can design an experiment. Right? So this was an important contribution, and his book, The Design of Experiments, was published in 1935 and went through multiple revisions and additions and whatnot. And I think the last time it was published, it was, in the late 50s. But at any rate, so how would you do this experiment? So he basically introduced the idea, well, we will set up an experiment in which there are 4 cups of tea served one way and another 4 cups served another way. We'll randomize the order in which the woman is handed the tea. All right, and this is an important part of the experiment. If you don't have random meaning you've got your population site and every possible outcome has a 1 divided by n chance of occurring, then your results can't be generalized. So random in statistics has a very specific meaning, and it allows you to make conclusions general to the population. You should be aware right away that very little of the criminal science, forensic technology and stuff involves sampling from the random population, right? So it's an interesting thing to think about. All right, so count the number of times that she correctly guessed whether milk was added first or milk was added later, right? And then you can count up the number of times she got 1 right, 2 rights, 0 rights, 3 times, or 4 times, right? And so you use your factorial combinatorial equation. And so there's 70 possible different outcomes. All right. Oh, by the way, she got all of them right. Yeah, okay. So from Fisher, we get the notion of what's called the null hypothesis. The null hypothesis is a general statement or a default position where basically you have 2 things and you say there's no relationship between them. It's if they came from the same population. No treatment effect, no difference. All right. After we run our experiments, we get evidence that can be said to support or reject the null hypothesis. And how you decide that it supports or rejects is a little bit of a discussion. The classical approach, which is a modification of Fisher's, will count every possible outcome, is what we would call the classical approach, or the frequentists, where you test the null hypothesis and then you equate it to a particular distribution of possible outcomes, and you count how many times your outcome comes relative to this theoretical distribution. Okay? This is where you hear the 5% criteria. So it's like if your p-value for your test is less than 5%, you would reject the null hypothesis. Okay, so let's kind of run you through a little experiment to see how this works. Okay? Do you have extrasensory perception? Can you guess what I'm thinking? So in the 70s, 1970s in particular, this was kind of a hot area of research. Those of you who are fans of the Ghostbusters movie, the first one, you'll recognize that they are testing for extrasensory perception, paranormal perception abilities. So can you read my mind? These are called Zener cards. Okay? And I am thinking about a card. So which one am I thinking about? The circle, the plus, the waves, the square, the star. How's my poker face? Ready? Okay. Yep, I was thinking about the plus. All right. So I've done this with my classes before, and so this is just one iteration of the results. All right. 6 of my students guessed waves. There was 2 students that guessed plus. So given that, is that an unusual expectation? All right. So given the number of cards in the deck, basically there's a 1 in 20 chance that somebody would pick the plus. All right. So you can't see it because my head's blocking my little R script, but what I can do, this is the box plot, and just sort of the not the box plot, the bar plot, all right? And take the number of observations on the y-axis, my categories on the horizontal axis, and you give these nice bars, and you can see that some observations were more common than others, so that's interesting. But is there something significant going on here? And so we use the binomial probability distribution, and a command in R, you just simply put D binom and 2, so that's the number of successes, the sample size, the number of trials, so that's 18, and the probability of success, I set it to be 0.2, just the 5 cards, right? Okay, so because I didn't shuffle, I didn't actually show 20 cards, right? I only showed 5 cards. So the probability comes out to be how likely would we see 2 students guessing correctly what I did? Well, about 17% of the time. So by convention, we'd say that's not an unusual observation, and we'd sort of move on with our life, right? Okay. So this is a screenshot of a place online, RDRR, that you can run code snippets. And then this is the same stuff in RStudio, just to show you kind of what it looks like. I think it looks a lot better on your computer. Okay. I would be remiss if I didn't mention something else about the history of statistics. A lot of these dudes, we wouldn't really appreciate them today. All right, you should know about Francis Galton, who is basically the creator of regression, linear regression techniques, or Carl Pearson, who introduced linear correlation as well as other correlation estimates. And then certainly Ronald Fisher is an absolutely enormously important person in the history of statistics. Analysis of variance, likelihoods, all those things traced to the brain of Fisher. All right. However, what I would suggest, often their motivations were they were card-carrying members of eugenics. You know eugenics, right? That's the idea that we should actively intervene to make sure that certain kinds of people don't have kids and other people we prefer do, right? And so Galton created the Eugenics Society in England, and certainly in the 1920s and 1930s, this was an enormously powerful group in the United States, for example. So what are you going to do? Their ideas, their statistics have outlived their political and moral, shall we say, issues. The statistics are enormously helpful and useful, but there is some history there about the people in particular that you should be aware of. Okay. Fairly quickly now, I want to kind of introduce you to the idea of experimental design. You don't do experiments in collecting evidence from a crime scene, right? But forensics is becoming a much embracing more experimental approaches. How do you know, for example, that no two humans have the same fingerprints, right? What's the evidence for that? All right, so lots of experiments are being done in forensics, and hopefully you get a chance in your program to do some experimental design work. So let's go. Okay, so you got to come up with a null hypothesis. So this isn't an experiment, but I thought I'd throw in this idea about thinking about hypotheses and match statistics, right? And so from a perspective of the jury, the null hypothesis is the defendant is selected randomly from a population. The alternate is that the defendant did the crime. Clearly, if we're to take classical statistical thinking about the null hypothesis, already the null hypothesis doesn't make a lot of sense. Obviously, the person on trial is not randomly selected in any way, shape, or form. And also, of course, populations are not infinitely large. And so those two things make it already different from classical statistic thinking. All right. So let's back up and be a little bit more general. So thinking about science, there's two kinds of research programs. Classic experiment means that you have control. And the control specifically not only is about the variables that you're interested in studying, but it's also about you have control about who receives the treatment. The researcher randomly assigns individuals to a control group or to a treatment group. Right? If you can do that, then the literature of statistics, as well as the philosophy of how do you interpret data and make inferences, collect evidence from that, says that if you've controlled, then you're on solid ground to establish cause and effect. One thing causes another to change. All right? That's the beauty of experimental approaches. Control, so therefore you limit the interpretation of the outcomes. You rule out some possibilities, and only some possibilities, some explanations are left over. All right? The other class of research are based on observational studies. And of course, most of what we know about humans are based on observational studies. I would hope you would appreciate immediately that you're not allowed to just simply put people into groups. Right? You're not supposed to do that. So observational studies means that the treatments were in effect selected by nature. So we can ask the question about the relationship between cigarette smoking and lung cancer without doing any experiments. We can simply look at population information. We look at different populations, and we can look at the association between cigarette smoking and how many people end up with lung cancer, right? And so the association is overwhelming. But there's no experiments to do that. It's unethical to take, a 20-year-old and randomly assign him to a smoking group. Okay? Just saying. All right. It's very challenging, and so I have typically the way you would teach this, you'd say, is that observational studies allow you to develop correlations, associations, right? They don't show cause and effect. I have the asterisk there to say, but this is the key thing about doing science. You don't say smoking causes lung cancer based on a single study. You get 2 studies, 3 studies, 4 studies, same populations, different smoking histories, etc., etc. And if you still come to the same conclusion over and over and over again, the risk of lung cancer is significantly elevated given exposure to cigarette smoking. At some point, it causes lung cancer, okay? All right. You know what I mean by cause and effect? Okay. It refers to the relationship between 2 events or 2 objects. Okay. In statistics, the null hypothesis is that the 2 events or 2 objects don't affect each other. The experiment that you're doing is trying to establish that there is a cause and effect relationship. I also note, just for historical reasons, in biology we're prone to also think about why things are because we're products of evolutionary history. So in particular, when it comes to thinking about DNA profiles, understanding ancestry, pedigree collapse, endogamy, those kinds of things have a bearing on your match statistics. And so that's the evolution part. The why questions are cause and effect at the ultimate level that you have to be aware of. Okay? And our method for establishing cause and effect is the scientific method. I won't go through all this. Okay, if you're interested in sort of the statistical characterization of that, it shows on the right. Okay, so just like we tried to justify why statistics, etc., let's go right off the bat and say, what's a good experiment? What are the characteristics of a good experiment? Okay, you got to have an interesting question. People have to care about the answer to the question. And I guess that's why, practically every week we get reports about, if you drink coffee, it prolongs life, or it reduces your chance of cancer, or it increases your risk of type 2 diabetes, right? We're always interested in those kinds of, they're not experiments necessarily, they're observational studies. They can be prospective studies in which people are assigned to, but generally they're not, right? But we're always interested in those. So I don't think those are particularly interesting questions. I like my coffee. Leave me alone. All right. The second part is, if you have an interesting question, that's fantastic. The reason I'm saying leave me alone about the coffee is I don't really think that they're particularly testable hypotheses. The effects of a little bit of caffeine, a little bit of the other chemicals in coffee expanded over a lifetime is pretty hard to separate all the other things that go on in a person's life. So how are you going to attribute health benefits to a single cup of coffee a day as opposed to exercising or not exercising, powerlifting or marathon training, practicing a musical instrument, reading all the time, watching movies, sedentary, etc., all those kinds of things. Whether you have people living in the house or you're just surrounded by cats, hard to control for all that. The control becomes you have to increase your number of subjects in your groups. And so these studies are enormous in order to be able to test for small differences. The other part is a good study includes efforts to randomize, okay? If you can randomly select your subjects, assign them to the different treatment groups, it allows you to control for many of the additional sources, excuse me, that may cause people to develop cancer, for example, right? And it controls for many sources of bias. Key characteristic of a good experiment: controls, placebos, all right? Humans get better. Humans change, sometimes irrespective of the treatments that are applied. And the last part has to do with eliminating sources of bias. So it's like if you have, I have something vested in coffee. I want to keep drinking my coffee. So if I'm going to be doing a study about coffee, then I pretty much need to protect against my confirmatory bias. I think coffee's fine, right? And so if I was to know who received coffee and who didn't receive coffee, all right, it's hard to rule out that even unconsciously I may sort of select data one way, interpret data one way that sort of reinforces my thinking, right? So the point about the scientific method is it recognizes that we all have biases, and so we try to control those biases by the design itself. So a single blind would refer to that the subjects themselves don't know what they're receiving, and a double blind means the folks interacting with the subjects don't know. Right? It doesn't mean no one knows what the treatment is. The analyst is going to know, right? But the analyst isn't working directly with the subjects. Okay. Let's clarify when you make your hypotheses. You do it before you start your experiments, right? So the clear thing about a hypothesis is that it's not just a question that's interesting, it's a question that makes specific testable predictions, and you do that ahead of time, so a priori, right? If you do that, it's part of the parcel of how to establish cause and effect. Disadvantage, well, what that means is that you often collect a lot more data than simply this primary outcome that you're interested in. And this is also to sort of hint that there's another approach to doing statistics. For example, gather as much information as you can, Google, and collect that information into your rows and columns, and then stick algorithms in there to see if they can pull out patterns of association, machine learning, right? Money's made doing that. It's just not an experiment or a test of a hypothesis. In fact, what it is what we call a posteriori method. You're making hypotheses based on the patterns that you're seeing in the data themselves. All right? And so the disadvantage is you should not be inferring causation from that. Okay. So the last slide in this is, can you think, how is DNA profiling like an experiment, or is it an experiment at all? All right, thanks for watching, and stay tuned to the next video.